We often forget the enormous power of our home star, the Sun. We are reminded of that power recently when NASA's Solar Dynamics Observatory recorded two powerful X-class solar flares coincidentally close to this year's vernal equinox. X-class flares are the most powerful, followed by M, C, B, and A. We orbit a remarkable star, remarkable in many ways. Many stars with the same classification as our Sun are quite variable. Variable in ways that would make life impossible on a hypothetical Earth with a similar orbit as our home planet. Our Sun is relatively benign in this regard, but it does exhibit a mild variability in energy output known with an 11-year cycle. Every 11 years, the Sun's energy output peaks. This mild variation is well understood and has been observed and scientifically documented for over 200 years. Coincidentally, astronomical beginning of spring this year, on the vernal equinox, a series of M and X-class solar flares has occurred, heralding the approach of the solar maximum in mid-2025. We begin showing the Sun in three separate wavelengths in the extreme ultraviolet part of the spectrum, color-coded to indicate temperature. In these opening frames, the light you see originated from much hotter layers well below the photosphere, emitted from gas with an effective temperature ranging from 50,000 to 2.3 million degrees and finally 12 million degrees. By comparison, the effective temperature of the photosphere, or the disk of the Sun, is a paltry 5,780. The Solar Dynamics Observatory is a space-borne solar observatory that has been in orbit since February 11th, 2010, continuously recording the Sun in 10 different wave bands, and was the first mission launched in the agency's Living with the Star program, a program designed to understand the causes of solar variability and its impacts on Earth. What we're observing as false color, bright pink plumes of gas is the highly charged superheated gas as it follows the powerful magnetic lines of force originating deep in the solar interior. It is these magnetic lines of force that breach the photosphere, interrupting the transmission of heat from the solar interior to the photosphere that causes sunspots, regions on the photosphere that are thus slightly cooler and appear dark by comparison. In the video segment that follows, we show the correlation of the sunspot groups and the solar flares. These solar flares were followed by a giant cloud of superheated gas and magnetic material known as a coronal mass ejection, or CME, a type of solar outburst made famous in 1859 and subsequently became known as the Carrington event, causing large-scale disruption of the newly developed telegraph systems of the day. We should expect now to see observable geomagnetic effects here on Earth in the coming days in the form of auroral displays and possible telecommunications interruptions. The Sun's internal dynamics are manifest during solar cycles, a period during which internal solar activity rises to a maximum and then to a minimum over an 11-year period. A rise in solar activity corresponds with a higher frequency of solar eruptions and an increase in sunspots. Since a new solar cycle began in December of 2019, we will start to see a rise in these types of eruptions, with the cycle's solar maximum occurring in the summer of 2025. The opening sequence combined light from three separate wave bands in the extreme ultraviolet part of the spectrum, originating deep in the solar interior, where the gas temperature is above 10 million degrees. All these images and video are color-coded to indicate wavelength, as ultraviolet does not have a color per se. Dark regions indicate no emission in the wavelength, waveband, or temperature being observed, and thus a gas with a specific temperature is visible, and that is what we observe. This video was produced from public archives available at NASA's Goddard Space Flight Center's Solar Dynamics Observatory web portal. Links to these data and images are available in the accompanying description. If you enjoyed this video or found it useful,